Professor Dave and Chegg here. It's now time to tackle another big topic, and that is thermochemistry. Thermodynamics is a branch of physics, and thermochemistry deals with specific areas of thermodynamics that are most pertinent to chemistry, namely those dealing with heat transfer. But in order to understand thermochemistry, we will have to define some concepts in thermodynamics. So let's start by looking at the most fundamental concept of all: energy.
Although the word energy is tremendously misused in common parlance, in science it means something very specific. Energy is the capacity to do work, whereby work means the displacement of an object. So for molecules to move around and do chemistry, this will require energy, which can take on an incredible number of forms, such as kinetic energy, the energy of motion, and potential energy, the energy of location. And in chemistry, we measure energy in joules. We may already be familiar with the first law of thermodynamics as describing the conservation of energy, essentially stating that energy is not created or destroyed, it only changes forms. There is a lot that can be gained from that explanation, but let's look at another way of stating the first law. The first law can also be summarized with the following equation, where delta E equals Q plus W. Let's understand that Q represents heat, or a transfer of kinetic energy between objects of different temperatures. W represents work, or force acting over a distance. And in this case, E represents internal energy, which is the total sum of all the possible kinds of energy present in a system. This equation tells us that the internal energy of a system can increase if heat is absorbed by the system, or if work is done on the system by its surroundings. And the internal energy of a system can decrease if heat is released by the system, or if the system does work on its surroundings. Positive Q corresponds to heat flowing in. Negative Q is heat flowing out. Positive W is work done on the system. Negative W is work done by the system. One type of work is called expansion work, or pressure volume work. This is when a system pushes against the pressure of its surroundings, such as an internal combustion engine, where some of the energy produced in the combustion of the gasoline goes towards pushing the piston in the cylinder. A state function is characteristic of a system that depends only on the current state of that system and not on how that state is reached. Internal energy is a state function, while heat and work are not state functions. If a quantity is not a state function, then it does depend on how that current state is reached. As an analogy, consider altitude versus distance traveled when getting to the top of a mountain. The altitude at the top of the mountain is a state function because whether you take a long, rambling path up one side, a more direct route up another side, or parachute down from above, the altitude at the top of the mountain will be the same. But the distance you travel to get there will certainly depend on the route you take. So altitude is a state function, whereas distance traveled is not.
It will not be necessary to understand concepts in thermodynamics with the rigor required in a physics course, but looking at energy at this fundamental level will help a lot as we continue to discuss energy in the context of chemistry. We have to understand that energy, perhaps in the form of heat transfer, is not a mystical property. It simply describes the motion of particles. Molecules that are moving more quickly have greater kinetic energy, and when heat is transferred from one object to another, it is simply that kinetic energy is being imparted by the faster moving particles onto the slower moving particles through collisions. These collisions are what cause chemical reactions, so understanding this will allow us to better understand chemical reactions. Professor Dave for Chegg. See you next time.